Hello, welcome to Trig class. We're going to be studying trigonometry this semester, so we better figure out what trigonometry is to start with. Well, if we break down the word trigonometry, trigono means triangle and metry means measure, so it's triangle measure. Now, even though we're just talking about triangle measure, we do bring in a lot of other ideas that relate to triangle measure, such as we're talking about circles, we're talking about identities, and many other things as well. Now, the history of trigonometry is really interesting, and the applications of trigonometry are very interesting as well. The history of trigonometry goes back probably about 2,300 years when our ancient antecedents were measuring and looking at the sky and trying to figure out what's going on up there with all those stars. They were interested in the motion of the planets and many other things, and they started to make observations, write things down, theorize, and develop some ideas that we still use today in our modern technology. So it's a really important area of study, and it's very interesting as well. It's applicable to not just astronomy, but many different areas: computer science, music, architecture, surveying, land surveying, mapping. I don't know if I mentioned chemistry yet, but so many different areas. And even if you don't think an area is involved with trigonometry, usually it shows up somewhere in there. My favorite part is the history of trigonometry and mapping. So back in the early 1800s, I think it was 1802, the British decided to do the Great Survey of India. And so what they did is they created a device called a theodolite, and they didn't make it up on their own, but they created a very, very large one in order to do this survey. So I'll show you a picture of this theodolite that was used. So this theodolite that's shown was one of the ones that was actually used to survey India, and the Great Survey of India, took almost 4 decades. And toward the end of this survey, they ended up in the northern part of India in the Nepal region, and they actually were able to determine the height of Mount Everest and determine also that it was the highest point on Earth. They overshot it by a couple hundred feet, and they continued to refine the measurements for this over the years until in like the mid-1900s they got it down to a pretty accurate value. Now, they actually used people called calculators to come up with these measurements, and they couldn't determine the height right away. They had to take all the measurements, take them back to where the calculators were working, and then determine those values. Now, this might look a little bit familiar to you if you're driving through a construction zone on the interstate. They have modern-day theodolites as well. So I'll show you a picture of those so you can see how they relate. So this is the modern-day theodolite here, and it's also known as a transit. They're not exactly the same, but they're pretty close. So you can see they're much more compact. The one on the left, the one that did the great mapping of India, was a half ton, and it took 12 men to carry. This one obviously can be carried by one person, a lot lighter, probably more accurate, easier to use, all those different things. But that's how our technology has evolved from the 1800s till today, and it still is evolving as well. So they use measurements, horizontal and vertical measurements, in order to determine the height of things, the level of things, the distance of things. And these are all very important tools that we don't necessarily use every day, but many people use every day to make our lives a little bit easier and a little bit better, and to build things that are useful and functional to us. So let's go ahead and get started talking about trigonometry. One of the first things that we'll need to know is the Cartesian coordinate system. We're going to be using this a lot. So the Cartesian coordinate system basically looks like two intersecting lines, and they intersect at a 90-degree angle. I won't mark the 90 on this particular one. And when we look at this Cartesian coordinate system, we need to talk about quadrants. So that way, if I say what quadrant I'm in, we all know the same value. We don't make up something along the way, and I renumber quadrants to be different. So when we're looking at this and we talk about our quadrants, we list the quadrants with Roman numerals. So this is quadrant 1. This is quadrant 2. They're going counterclockwise. Quadrant 3 and quadrant 4. So we need to be able to talk about these quadrants in order to talk about the location of an angle. Now, there's 2 different types of angles that we'll be looking at, positive and negative. So when we talk about a positive angle, we're talking about starting at a point. So this is the initial side, and then rotating counterclockwise through to the terminal side. So this is the initial side, and this is the terminal side. And this amount of movement from the initial to the terminal is the degree measurement. So this one might be, let's say, here we are at 90 degrees at the vertical. So we'll say maybe this is 110 degrees, okay? And it lies in the second quadrant. Well, I can also talk about negative angles that also start at an initial side and end at a terminal side. Now this one is moving clockwise. So this is a clockwise, and this would be a negative angle. And this is the symbol that we'll use for angle. It's an angle with a slash through it, like a curve. And again, it starts the initial, it ends at the terminal as well, but it's rotating in the other direction. So this one might be a negative, let's say 150. This would be a negative 180 if it went clear to the vertical here. So positive and negative angles, it's important to know the difference because it will be coming up a lot. A couple of other things to be aware of in our Cartesian coordinate system that we talk about are some common angle measures, which I'm sure that you know, but I want to review them real quick. So if we had an initial side of an angle and it never moved, that would be a 0 degree rotation. If it moved to the vertical here, that would be 90 degrees. If it moved clear across, it would be 180. Here would be 270. And if you moved clear to where the initial side terminated as well, it would be 360 degrees. Now, even though this initial and terminal end up in the same point, the amount of rotation is different between a 0 and the 360, even though the location is the same. So a couple things to remember. Now we can keep rotating as well, and then we'd get 360 plus 90, 360 plus 180, and keep going round and round infinite number of times. We can also move in the opposite direction. If we moved in the opposite direction as a negative angle, this would be a negative 90 degrees. This would be a negative 180 degrees. This would be a negative 270. This would be a negative 360. Okay, so those are going to be some very important ideas that we'd be able to snap those numbers off and talk about those angles. These are called quadrantial lines or quadrantial angles because they land right on the line between two quadrants. So quadrantial lines or quadrantial angles. Now you'll see what we have here. It ended up being very important with the 90 and the 180. So I want to talk about that a little bit more. There's two different types of characteristics that we want to talk about. First of all, we have complementary angles. Complementary angles basically mean angles that sum to 90 degrees. So if we were looking at complementary angles, I'm just going to look at this first quadrant right here. We could have some angle alpha right here, and then this angle beta would be the complement because it would force it to sum to 90 degrees. So they sum to 90 degrees. Now supplementary angles are similar, but they sum to 180 degrees. So 180 degrees is a flat line. So if we were to be able to look at the Cartesian coordinate system again, we can see here that this is our 180 degree. So if we had two angles, let's say we had another angle alpha, our angle beta would have to be what forced it to this 180 degrees over here. Okay, so complementary angles sum to 90, supplementary angles sum to 180 degrees. Important to know. We'll use that a lot in this particular homework section. So we can use these ideas to find complements and supplements of angles. For instance, we can find the complement and the supplement of, let's say, 29 degrees. Okay. So first of all, let's work with the complement. So the complement, remember, has to sum to 90. Now a lot of times you'll see a 90 degree mark, this little corner to indicate that that's a 90 degree angle. Well, 29 degrees would be, if I started, this is 90 degrees, remember the complement. So the angle that we're interested in is 29 degrees. So I'd start here with my initial side, and this is just graphing an angle. And then I want to go to my terminal side. Well, half of 90 would be 45. That would be right about here. 29 is about a third. So if I go about a third of the way, so let's go ahead and find the complement. And let's do 20 degrees and 21 minutes. So I should go back here and amend our notes over here just to clarify. So this is degrees, would be something like 29 degrees. Let's do 30 minutes would be a single tick mark, and 15 seconds would be the double tick mark. So those are the notations that we use. So let's find the complement to 20 degrees, 21 minutes. So if we look at 20 degrees, 21 minutes, there's a couple different ways that we can do this. We know a complement is 90 degrees. I should be able to rewrite 90 degrees as 89 degrees and 60 minutes. And the reason we're splitting this down into 60 minutes is up here, I'm going to 60. And then I can subtract 20 degrees, 21 minutes. So if we look at our 89 minus 20 here, that would leave us with 69 degrees. And then 60 minus 21 would be 39 minutes. This should be a minute mark. So 69 degrees, 39 minutes would be the complement. So we kind of look at that as just taking 90 degrees and rewriting it in degrees and minutes. Let's go ahead and find the supplement. Let's do the supplement to, let's do 21 degrees, 29 minutes, and let's go down to seconds here, 32 seconds. So if we break this down to 29 degrees, or sorry, 21 degrees, 29 minutes, and 32 seconds, I would want to think about rewriting the supplement, which is 180 degrees, in degrees, minutes, and seconds as well. So if we start with 180 degrees here and start breaking it down, you would think, well, that's 179 degrees and 60 minutes. And that's true. But the problem is we need seconds here as well. So in order to create our seconds, we need to break it down one more level. 179 degrees, 59 minutes. So we need to take one of those minutes and convert it to seconds. And now we're ready to subtract. So I'd have minus 21 degrees, 29 minutes, and 32 seconds. So here we'd have 7 minus 2 is 5, 158 degrees. So that works. 59 minus 29 is 30. And I keep making the degrees here, and they're minutes. And then 60 minus 32 would be 28 seconds. So this would be the supplement in degrees, minutes, and seconds. So a couple of things to keep track of that I wasn't. I was using the wrong symbol here, degrees, minutes, and seconds. Make sure you break off the degrees with the single tick mark and the seconds with the double tick mark. You can also add and subtract just like we were doing here with degrees, minutes, and seconds. So an example of that is we could take something like 59 degrees and 12 minutes and add that to 71 degrees and 44 minutes. Well, adding these together, 4 plus 2 is 6, so I have 56 minutes. And then over here, I have 130 degrees. So adding these two together, I'd have 130 degrees, 56 minutes. Now, part of the problem that I'm going to come up with here, if I'm adding and I get more than 60 minutes, is I'm going to have to convert that into a degree. So an example of that might be something like 22 degrees, 40 minutes, plus 33 degrees, and let's say 25 minutes. So if I'm adding these, here I have 65 minutes, and over here I have 55 degrees. But this is more than a degree. So this is 1 degree, 5 minutes. So this would be 55 degrees plus 1 degree plus 5 minutes if you want to think of it like that. So 66 degrees, 5 minutes. So whenever you have more than a minute that could, or more than 60 minutes that can convert to a degree, or more than 60 seconds that can convert to a minute, you need to do that. We always want it simplified as far as possible. Now we could also look at some subtraction problems with degrees, minutes, and seconds. So for instance, we could have something like 51 degrees, 21 minutes, minus 22 degrees, 56 minutes. Now we notice right away that we have a little bit of a problem here, because I can't take 56 minutes from 21 minutes. So we're going to do like the old-fashioned borrowing we used to do back when we learned addition and subtraction. We're going to cross this out and make it 50 minutes. So I'll have 50 minutes over here. And then I'm going to add 60 minutes and combine these. So when I combine these, I'll get 81 minutes. And now I should be able to subtract the 22 degrees and the 56 minutes. So again, when I subtract 50 minus 22 is going to give us our 28 degrees. And then our 81 minutes minus 56 minutes will be 25 minutes. So we're borrowing just like we used to, but instead of borrowing tens and hundreds, we're usually borrowing 60s in terms of 60 minutes in a degree or 60 seconds in a minute. Now I can also convert these back and forth from degrees, minutes, and seconds to decimals. So let's go ahead and look at converting. So let's go convert degrees, minutes, seconds to decimals. Now this is going to be pretty easy because we already kind of know what the ratios are here. So let's convert, let's say 26 degrees, 8 minutes, and 5 seconds to decimals. Well, the way that this is going to look is 26 plus 8 minutes, but that's 8/60th of a degree. Okay, then next we'll have 5 seconds, and we're converting everything to degrees here, so I need to remember that that's 36/100ths of a degree. So when you plug this into your calculator, and then of course we need to always make sure that we round correctly. Let me pop open a calculator here. So let's get these side by side. Let's go 26 plus 8 divided by 60 plus 5 divided by 3600. So I get 26.1347 and a repeating 2. So 26.1347 and a repeating 2. So 26.1347 and a repeating 2. So usually we're asked to round this to thousandths, let's say. And again, always read your instructions in my math lab. So here's our thousandths position. So the 7 would create a 5 here, or round that up to a 5. So this would be 26.135 degrees. So that's an example of converting. Now I popped the calculator open, so I want to make you aware that on your calculator, hopefully you have a TI-84 plus. They usually have this nice little fraction key. So if you notice, I use the slash key here. Well, if you go to alpha y equal, there's this fraction option, and I could have written this as 26 plus, and then in the numerator, just to make sure I have everything correct and I don't have to worry about parentheses and stuff, I could do 8 divided by 60, and then plus alpha y equals that nice fraction key. It's not extremely useful for this problem, but it will be really useful to know about this fraction key throughout the class. So I just wanted to show it to you now. And notice it gives me, because I entered it as a fraction, it returns as a fraction. If you enter it as the division, it will return as a decimal. And then to convert that to a decimal, I just go math frac. Except I didn't want a frac, I wanted a decimal, so let's try that again. Math decimal is the second option, and it converts it for me. So using this fraction key, that's going to be a really important idea. And again, that's the alpha y equal. And you'll see that option right over here in this key sequence. So that's right here under the alpha y equal. That's what creates that fraction. Okay, so let's convert the other way. Let's go decimals to degrees, minutes, and seconds. Okay, so for converting decimals to degrees, minutes, and seconds, what we need to do is think about what we have in terms of proportions. So we could have 35 degrees, 31 minutes. Well, we know that this is going to be the full 35 degrees. And then I need 31 minutes, sorry, I keep making the degree mark again, 31 minutes. That's going to be 31% or 0.31 of 60 minutes. Okay, so when we plug this into our calculator, I'm going to get 35 degrees plus 18.6 minutes. So this will break out into 35 degrees plus 18 minutes plus 60% or 0.6 of our seconds. So again, degrees, minutes. Okay, now we're doing seconds. So this will end up being 35 degrees, 18 minutes from our first part, plus 0.6 times 60 is going to be 36 seconds. So this would be 35 degrees, 18 minutes, 36 seconds. Okay, that's how that would convert. So what we're doing is we're always talking about parts. So to start over again up here, we can look at taking this 31 degrees and saying, oh, that's 31% or 0.31 of 60 minutes, which 60 minutes is part of that degree. It's 1 degree. So then we take the 0.6 and we say, okay, well, that 0.6 is 60% of a degree, and a degree is equal to 60 seconds. So that's how we end up breaking these down. So these are pretty straightforward to convert, and again, you'll need your calculators obviously for that. And there's a spot on your calculator that will convert these for you. Let me see if I can remember where it's at. So if you go up into here to second angle above the apps, here you see your degrees and your minutes. And if we scroll down here, you'll see your DMS, degrees, minutes, second. So you can check a lot of these answers using that, but again, checking your answer isn't the same as showing your work. And remember, everything you're graded on for your exams is showing your work. So if you just write down an answer, there's going to be no credit for that. So make sure that you know how to show your work and do your work. And then, of course, feel free to use your calculator to check your work. Now, another thing that we can talk about, or questions that we can answer, would be angles that are coterminal. So the idea of a coterminal angle would mean, kind of back from when we were spinning around the unit circle at the very beginning here, if we looked at a measure of, let's say, 761 degrees, that's clearly more than 360 degrees. So 360 degrees would take us to here. Another 360 keeping going would be at 720. And so if I'm talking about 761, I took away a 360, and I took away another 360, and so that left us with 41 degrees. So that would mean that I would be left with 41 degrees here. So that's called coterminal. It means it ends at the same point, but the amount of rotation could have been different. So if I talk about find the angle of least positive measure in degrees that is coterminal with A, that would be 41 degrees. So what I did, because it was a positive angle, I just subtracted 360 degrees as many times as I could, and to see what was left was the 41 degrees. So that's a quick way that we could look at something like that. Now there's also other problems that we can solve that are similar to this. We could be looking at problems with negative angles. So for this one, we're saying find the angle of least positive measure, so we have to have a positive measure angle that is coterminal with A. Well, first of all, to get started with this, we better graph negative 294 degrees to kind of give us a visual where we're at. Well, it's negative, so we're going to start and move in this direction. This would be negative 180. Here we'd be at negative 270, so again, negative 90, negative 180. This would be a negative 270. So I'd keep going past that a little ways. And this leaves us at negative 294 degrees. Well, what I'm looking for here is the angle with least positive measure. It's coterminal, so it's ending at this point. So if I wanted to figure out what that was, there's a couple different ways I could do this. First of all, the distance from 270 to 294 is 24 degrees. So if I wanted to look at this in terms of being in quadrant 1, I could look at this as 90 degrees minus 24 degrees to get my angle of least measure. So this would leave us at, what, 66 degrees. That would be my angle of least measure that's positive and coterminal with the angle that we just graphed of the negative 294 degrees. So that would be one way that we could approach this. I could have also just taken 360 degrees minus the 294 degrees to get my 66 as well. But it kind of depends on where this lies in space in terms of the quadrant. So I think it's always a good idea to graph first and then logic your way through that. Either way, a graph is very, very helpful. Now, a lot of times when we're working through these problems, we can include things like degrees, minutes, and seconds in these problems. So you have to be careful about kind of incorporating the other information we've learned with degrees, minutes, and seconds, the idea of coterminal, meaning sharing the same terminal side, and then also with decimals and converting back and forth. So we can combine all these types of things. Another thing I want you to keep in mind are problems that we're talking about generating angles. So a lot of times I want to generate a terminal side using a particular angle as a starting point. So let's look at an example like that. So this one says, find the next two positive and the next two negative angles that are coterminal with the given quadrantial angle. And I think the quadrantial angle that I would like to use in this case is alpha equal, let's do negative 270 degrees. So we get to work with negative angles a little bit. So I think the first thing that we should do is graph negative 270 degrees. So here we are at negative 90, negative 80, negative 270 degrees. So find the next two positive. So let's find our positive coterminal angles. Well, the positive is going to be easy here because I'm just coming up. It's called a quadrantial angle because it is landing on a quadrant line. That would just be 90 degrees. So I'd have 90 degrees. And then my next one would be 360 degrees more than that 90. So our next one would be our 90 degrees plus 360 degrees. So our two angles that we want to enter then, and these are what the questions look like in my math lab. So there's an answer blank that will say enter the angles separated by the comma, do not include the degree mark. And then 90 plus 360 here would be 450. So the way that I'd enter these in my math lab, MML is abbreviation for my math lab, is 90, 450. So let's go ahead and look at the negative angles. So let's find two negative angles that are coterminal with the given quadrantial angle. Well, we're already at a negative 270. So what I'd want to do is I'd want to come and I'd want to hit this again, and that's another 360 spin around. So it'd be a negative 270, move 360 degrees again in the negative rotation, and negative 270 plus 360 looks like it'd be a negative 630, negative 630 degrees. So then I'd start at a negative 630 degrees, and I'd do another negative spin, which would leave me at negative 990. So again, in my math lab, I enter this as negative 630, comma, negative 990, separated by commas, and the degree mark is already on the answer blank, or they ask you not to include it. Just make sure you always read the instructions there. So again, once we know these things, 360 degrees and a full spin, the quadrantial angles, we can also do this with degrees, minutes, and seconds. So I'm kind of combining all of these ideas into some different problems. So you can mix and match these. Let's go ahead and use the same idea that we just were talking about, making another full spin. And let's go ahead and write a generic expression then that would be able to generate all the angles that are coterminal with a given angle. Now here we're looking at 180 degrees. So let's go ahead and sketch this out. 180 degrees would be this angle right here. This is the initial side. This is the terminal side. And if I wanted to find every single coterminal angle with here, what I could do is I could realize that that's going to happen when I do another 360 degree spin, and I could do another 360 and another 360. So every coterminal angle is created by another 360 degree spin. So the way that this would look is I would add 360 degrees each time. And since it's an integer, I'm going to use the letter n to represent an integer value. So this could be 0, 1, 2, 3, and this is basically the number of spins. I could also move in the negative direction, and I could move, let's get a different color here. I could start here and moving in the negative direction. I could go a negative 360 and hit this spot, a negative 720 and hit this spot, etc. So this is how I'd represent that generic expression that would generate all angles that are coterminal with that given angle. So it's the same idea that we did above, but in this example, we're just calling it this generic n. Okay, let's go ahead and look at one last problem type from this section. So I want to make sure that you see all the different types of problems. Now the problems that I'm popping in here are from my math lab, so they're the same types of problems that you'll see there. So this last example, we're going to be talking about revolutions. So we're talking about spinning around a circle, and we're talking about amount of rotation. So to me, this is kind of a unit analysis. This would be like from chemistry when you were converting, and when you're converting different things from miles per hour to the miles per second, etc. So if we talk about 800 rotations per minute, I'm going to call that rotation as a revolution. That means it's a spin around the unit circle, spin around the circle. And that's in 1 minute. It says, through how many degrees does a point on the edge of the tire move in 1/7 of a second then? Well, what we want to know then is we want to convert things from minutes to seconds and from revolutions to degrees. So I could look at this and I could think, well, I can convert minutes because there's 1 minute is equal to 60 seconds. And then I could talk about revolutions, and there's 360 degrees in 1 revolution. Okay, so that would work pretty slick. Now the only thing I don't have here is my last little bit here. What's happening in 1/7 of a second? So I could take this times 1/7 of a second. Now let's look to see if our units cancel. I have revolutions, I have minutes, I have seconds canceling, and I'm left with degrees, so this looks good. So let's go ahead and grab our calculator. 840 times 360 divided by 6 divided by 7. So I'm going to clear this out. So I have 840 times 360 divided by 60. And I'm going to enter that and then divide that by 7. You can use your fraction key as well, and I get 720. So this is 720 degrees. So in 1/7 of a second, it's rotating 720 degrees, which is 2 spins around the unit circle, because 360 plus 360 is 720 degrees. So that's the kind of problems that we can solve using our knowledge of the unit circle, degrees, minutes, and seconds, the number of degrees in a circle, etc. So for your first homework assignment, make sure, and when you're working in my math lab, that you read the directions carefully. Round is indicated. Enter the answers as they indicate, like with commas and without degree symbols. So take your time to read those instructions, and underneath the little box, they'll also have additional instructions about how to enter your answer. If you have any questions while you're working, please feel free to let me know. You can just send me a screenshot of your work or a screenshot of the problem and shoot me a text, and I'd be happy to help out. Good luck.